Welcome to the second module of fire and explosion. Up till now, we have studied about the fire and explosion, the basic definition of fire and explosion, different type of fuels which are responsible for fire. We have discussed about the different modes of heat transfer through which fire or heat generated being transmitted to some other part. And we discussed about the fire triangle, which is responsible for fire propagation, initiation, etc. Now, in this module, we will discuss about the flammability characteristics, which is extremely important, that how what are the different parameters required for flammability, minimum oxygen concentration, minimum ignition energy, adiabatic compression, auto ignition temperature, and various sources of ignition. Now, flammability characteristics. Before we discuss the flammability characteristics, let's have a look about the flash point. Now, flash point, this is the property of a material used to determine the fire and explosive hazard. This is the lowest temperature of a liquid at which it gives off enough vapor to form an ignitable mixture with air. So, whenever there is an ignitable mixture, there are another criteria which needs to be fulfilled before any particular flammable mixture catches fire. We will discuss in the subsequent slide. Now, generally this flash point increases with increasing pressure and it needs to be determined experimentally. Now, there are different methods for determination of flash point, like open cup, closed cup. Now, open cup flash point is a few degrees higher than the closed cup flash point. And one point should be remember that whenever we report the flash point, then it must be reported that through which method it was determined. As far as liquid fuels are concerned, another point is the fire point. This is the lowest temperature at which a vapor above liquid will continue to burn once ignited. The fire point temperature is higher than the flash point temperature. There are certain other things which are proposed by National Fire Protecting Agency, United States, about the flammable liquid, the liquid which with a flash point less than 100 degree Fahrenheit. Now, this type of characterization is essential whenever we need to design the protective equipments, we need to design the fire retardancy aspect of any process. Then we must know that which liquid is flammable and which is not. Then combustible liquid, the liquid with a flash point greater than 100 degree Fahrenheit. Now, let us have a look about the flammability limit. We must know that which is the flammable mixture, which mixture can combust. So far, when mixture is having the higher concentration, then definitely the corresponding amount of oxygen would be on the lower side, then definitely the mixture would not be ignitable. So, question arises that what are the limit and how we can ignite the combustible mixture. So, people have proposed two type of limit, lower flammability limit and upper flammability limit. So, there is a usually range of composition of a flammable vapor and air where the combustion occurs. Now, one thing must be remember that for any kind of flammability, for any kind of formation of combustible mixture, there must be a fulfillment of stoichiometric demand. Let's have a hydrocarbon combustion formula of CH4 plus twice O2 Now, once these two things, with methane and oxygen, they are in the stoichiometric demand, only then the fire will catch. So, in other words, if there is too little fuel and which is not enough to burn, that is covered under the head of lower flammability limit. And if too much fuel, that means the fuel concentration is on the extremely higher side and which is not duly supported by the supply of oxygen, then again there would be a difficulty in fire. So, in this particular plot, you can see the concentration of flammable gases in volume percent and explosion pressure. So, these two are lower explosive limit, this one, and upper explosive limit. Sometimes LFL and UFL, they are called lower explosive limit and upper explosive limit. So, whatever is inside this plot, that is the combustible. We will discuss in the subsequent slides in detail. Now, the flammable and explosive limits the range of composition of material in air which will burn, that is upper flammable limit, lower flammability limit. Sometimes it is termed as higher explosion limit and a lower explosion limit. Now, measuring these limits for vapor air mixture of known concentration are placed in a specially designed closed vessel apparatus, and then ignition is attempted. The maximum explosion pressure is measured. Now, usually test is repeated with different concentration to establish the range of flammability for the specific gas, because sometimes it is advisable that you must not able to form these type of mixture within these LFL and UFL. So, if you wish to work in the safer range, then you need to have your mixture either in this range or in this range, because this range is a flammability region. Somehow, if by any source it catches the source of ignition, then definitely there are chances that it will ignite. So, if you wish the fire to be placed there, then or deliberate attempt, then your mixture should be in this range, and if you don't wish, then definitely you have to take certain attempts so that the mixture doesn't fall in this flammability region. Now, whenever we wish to form any kind of flammability relationship or flammability chart, we should not forget the importance of flash point, auto ignition temperature, etc. Because sometimes if your mixture is beyond this range and by any means it acquires sufficient amount of energy, then it will automatically auto ignite, and then the things would be more dangerous compared to the previous one. So, whenever you wish to form or we are having any hydrocarbon or any flammable liquid or flammable gas with you, then it is important that you need to know that what is my LFL, what is my UFL, and what is the flash point and auto ignition temperature. Sometimes it is again equally important to form the different type of flammability diagram, so that you can have the flammability mixture line. Now, here you can find this particular diagram is very interesting. The reason is that you are having one fuel, you are having one oxidizer. Apart from this, you are having an inert. Now, question arises that why do we use inert? The reason is that we are having LFL and UFL in place. That means, and suppose I am working in a hexane environment. So, definitely we do not want to have a combustible mixture, that is the combination of hexane vapor plus oxygen. And somehow, because if by any means you are not in a position to avoid such kind of mixture, then definitely your attempt should be like this, that you must introduce some inert so that it fall either way. Either it goes lower to the LFL limit so that this mixture doesn't in place, or somehow if you wish to increase or if you are in a position to increase the supply of fuel, so you enrich the combustible mixture in such a way that the concentration of methane is on the higher side. But remember, this particular aspect is extremely dangerous. The reason is that if by any chance or by any leaking sufficient quantity of oxygen or air is entrapped within the zone, then definitely it will form a combustible mixture. So, you must know that how much quantity of inert material is required to make the things safer. For this, these type of diagrams are quite beneficial. Now, this is the particular diagram for the methane. Here, you must, this particular region is the flammable region. Now, here you can assess that what should be at what concentration of methane and at what concentration of oxygen, because you can see the stoichiometric line. So, your attempt should be like this, that you must introduce nitrogen in such a way so that it does not cross the LFL mark. So, this is another line that is depicting the limiting oxygen concentration. The limiting oxygen concentration, it says that volume percent of oxygen below which combustion can't occur. That means there is no adequate supply of oxygen to meet the stoichiometric demand. If you recall the previous chemistry formula, CH4 plus twice O2, that means if you are increasing the amount of nitrogen, that means definitely it will not cross this limiting oxygen concentration mark. Now this is the safer zone. So that's why whenever you are having such type of scenario, you must calculate that up to how much quantity of inert material is required so that it does not cross this LOC barrier or it does not cross the LFL line. This is again for the ethylene hydrocarbon again, sorry. Now here again you can see the LOC, and this is our air line, that means the supply of air. Oxygen is automatically being extracted from the air. So ethylene, the combustion of ethylene requires this quantity of oxygen. So by any means of introduction of nitrogen, if you introduce certain quantity of nitrogen, that means the concentration of oxygen or limiting oxygen concentration is on the lower side, or the LFL is on the lower side, so that the mixture doesn't form the combustible one. Now question arises that once we have discussed the flammability limit, what are the parameters those who are affecting these flammability limits? So there are three different parameters, that is the concentration of inert material, we have discussed through two diagrams, the temperature and the pressure. So these three are the major parameters those who are affecting the flammability limits. Now let us have a look that how these LFL is determined and what are the different mathematical equations applied for to govern these LFL. So lower flammability limits for several common substances we need to determine, and usually it is advisable to determine those limits through experimental process. However, if you have adequate knowledge of flash point, then LFL you can be estimated through the flash point. Now here is the formula, that LFL equal to vapor pressure at flash point divided by 760 mercury. So determination of vapor pressure using the Antonyi equation. Antonyi equation is a very famous equation in chemical engineering thermodynamics. So you can determine the vapor pressure through which you can assess that what will be the theoretical LFL of that particular substance. Now if one have a mixture of flammability components, lower flammability limit or LFL mixture can be calculated using the Le-Chatelier's relationship. Now this Le-Chatelier's relationship is that LFL mixture is equal to 1 upon summation of I equal to 1 to nth component Yi upon LFLi. This LFLi is the flammability limit for component I, and Yi is the mole fraction of ith component on combustible basis. Remember this particular combustible basis, because inert material can't take into consideration, and n is the number of combustible species present in that particular mixture. Similarly, you can calculate the upper flammability limit too for the mixture using again the same Le-Chatelier's relationship. UFL mixture is equal to 1 upon again summation I equal to 1 to n and Yi upon UFLi. Other designation like this is the mole fraction, ith component, and on the combustible basis. Now for determination of these LFL and UFL, there are certain inherent assumptions we have taken. The inherent assumptions, though they are theoretical one, but still we cannot overlook their importance. The product heat capacities are constant, though I can't say precisely because the temperature is on the varying side. The number of moles of gas is assumed to be the constant. The combustion kinetics of pure species is independent and unchanged by the presence of other combustible species. The adiabatic temperature rise at the flammability limit is the same for all species, reasonably valid at LFL and less so that of UFL. So because the temperature variance and mole they do affect in the determination of LFL and UFL. So earlier in earlier slides we have discussed that the LFL and UFL both are having impacted by temperature. Now these are the formula through which you can assess the effect of temperature on LFL and UFL. And usually the standard denotation of or standard representation of LFL and UFL is 25 degrees Celsius. So if you wish to determine the LFL, UFL at say 80 degrees Celsius or 90 degrees Celsius, then you can easily utilize these two formula. LFL at a specified temperature T is equal to LFL 25 into 1 minus 0.75 T minus 25 upon delta Hc. Delta Hc is the heat of combustion of component T is in degrees Celsius, and this can be easily calculated or this can be easily available in various handbooks. Similarly, UFL at specified temperature is equal to UFL at determined at 25 degrees Celsius into 1 plus 0.75 into T minus 25 upon delta Hc. Now theoretically, you can determine all these LFL and UFL so that you can anticipate that suppose if I wish to run the reaction at say 120 degrees Celsius, then definitely it is my first right to know that what would be the LFL and UFL at the specified temperature or at my working temperature. So these formula or these mathematical relationships, they are quite useful. Now the last effect is the flammability limit, the pressure effect. Now LFL is usually not affected by pressure except a very low pressure, and usually except at a very low pressure the chances of ignition are very rare. So UFL does depend on the pressure, and this is the mathematical relationship through which you can predict the pressure of pressure effect on UFL at particular point of time. So UFLP is equal to UFL plus 20.6 into log P to the base 10 plus 1, and pressure P is in megapascal absolute. So the procedure is to correct for the temperature prima facie, then the correct for pressure, and then calculate for the mixture. So you are having the wide spectrum through which you can assess that what would be the LFL and UFL of the mixture and individual component. Now let's have a look about the minimum oxygen concentration. See, we talked about this importance of oxygen in the previous slides, that the mixture or the fuel must be in a stoichiometric presence so that it can catches the fire. That means you require a minimum oxygen for any kind of ignition, for any kind of fire. So LFL is based on air, but actually it is the oxygen that is important. Often it is in industry, they inert to dilute the oxygen concentration so that it is just below the LFL range. So below the minimum oxygen concentration, the reaction cannot generate enough energy so that it cannot meet the requirement of delta Hc to heat the entire mixture to the extent required for self-propagation. The MOC in previous layers has also been called the limiting oxygen concentration. The maximum safe oxygen concentration is MSOC. Sometimes you may find in literature that it is reported in terms of MSOC. So LOC depends on the inert gas species. That's why if you recall in the previous slides that we have discussed the nitrogen effect of nitrogen in those diagrams. So usually it depends on the inert gas species. The LOCs has the unit of a percentage of moles of oxygen in total moles. Now this is the mathematical relationship or a derivation through which you can calculate theoretically the minimum oxygen concentration. So minimum oxygen concentration is equal to moles of fuel divided by moles of fuel and moles of air multiplied by moles of oxygen divided by moles of fuel, and this particular thing is LFL. So MOC or minimum oxygen concentration is equal to LFL into moles of oxygen divided by moles of fuels. So need to balance the stoichiometric relationship. This is the generalized hydrocarbon combustion relation, CmHxOy plus ZO2 equal to mCO2 plus x upon 2 H2O. Now through which you can calculate this one. Z is equal to m plus x upon 4 minus y by 2. Z is equal to moles of oxygen divided by moles of fuel. So through which you can easily calculate the minimum oxygen concentration. Now we have talked about the essential requirement for a combustible mixture. Now let us have a look about the minimum ignition energy. The knowledge of ignition limits of a combustible gas mixture is of importance in many combustion systems. Now, in order to successfully ignite a flammable gas mixture, sufficient amount of energy is needed. The smallest amount of energy that results in the successful ignition is known as the minimum ignition energy. Now, this is the standard definition. Without this minimum amount of energy, you cannot ignite the mixture. So, this is the minimum amount of energy required to ignite a particular mixture. Now, in other words, the minimum energy that can ignite a mixture of a specified flammable material with air or oxygen measured by a standard procedure. Now, this is the scientific definition of MIE. Now, the minimum energy input in a single line aspect, you can always say that minimum energy input needed to initiate the combustion. Most hydrocarbon, they are having very low minimum ignition energy, that is around 0.25 millijoule, whereas a spark walking across the room is around 22 millijoule. So almost 100 times greater than as required for this one. That's why whenever you visit the refinery or any hydrocarbon plant, it is always advisable not to use the shoes which are having the shoe nails or iron nails. So we always assume that an ignition source will exist. Only thing is that we need to minimize the impact of this source of ignition. Now, minimum ignition energy requirement varied with the mixture composition, fuel type, pressure and a temperature. So, the lowest amount of energy required for the ignition depend on the major variables. Those are dependent on temperature, percentage of the combustible and the different type of compound which are in question, because the hydrocarbon, those who are having the lower molecular weight, it can easily catch the fire. Now, next is the adiabatic compression, and this is most common phenomena in hydrocarbon combustion, and especially you can easily visualize this particular phenomena when you are using your motor car and scooter which is having too high temperature, or if you run across say 500-600 kilometers and without giving any rest, then the temperature will rise up. So, this is an additional means of ignition is the adiabatic compression. So, when gases are compressed to an adiabatic temperature that exceeds the auto ignition temperature, they heat up and can ignite. This is how the diesel engine works, also the cause of knocking in various gasoline engine. So, you can calculate the adiabatic temperature by this standard thermodynamic relationship. Tf is equal to Ti into Pf upon Pi to the power gamma minus 1 upon gamma, and T and P are in the absolute form. So, you can calculate, and if this temperature is just above your auto ignition temperature, then definitely you need to take certain attempts to minimize the effect of auto ignition. Now, auto ignition temperature, because we have discussed this auto ignition temperature in adiabatic compression, then again it's a prime duty to have a look at what is auto ignition temperature. So, the auto ignition temperature of a substance is the lowest temperature at which it is spontaneously ignite in normal atmosphere without an external source of ignition. So, in other words, the temperature at which the vapor ignites spontaneously from the energy of the environment. Now, see, if you compare with the adiabatic compression, then the temperature at this paraphernalia is on the higher side than auto ignition temperature, and if sufficient quantity of oxygen is available, then definitely it will ignite. Now, this AIT is a function of concentration and volume of the vapor, the pressure of the system, the material in contact and size of containment. Now, we have discussed various aspects of flammability characteristics, and without the source of ignition, you cannot imagine the fire, whether it is in the positive sense or in a negative sense. So, what is ignition source? So, an ignition source is a process or event which can cause a fire or explosion Open flames, spark, static electricity, and hot surfaces are all possible ignition sources. An explosion can occur when flammable gases or vapor in the air come in contact with the ignition source. And remember one thing, that ignition sources are almost free and available everywhere. We have collected some statistical information about the ignition sources. This is based on the accidental investigation. So electrical motor or wiring of motor, they causes almost 23% of accident. Smoking 18%, friction, bearing or broken parts almost 10%, overheated materials abnormally at high temperature almost 8%, hot surfaces, burner flames, combustion, spark, spontaneous ignition, cutting, welding, etc. So they all contribute. The basic purpose of this particular table is that you must know that what is the impetus of different variables through which, and what is the gravity of those variable or sources of ignition, those who are incorporating in terms of accidents. So you must aware that these can be very dangerous. Now, these sources of ignition must take adequate precaution to prevent the ignition of flammable vapors. They are some of the casual sources of ignitions are smoking, electrical equipment. So that's why if you go to a refinery, you are not allowed to smoke inside the refinery. The heaters, the contractor tools and equipments, arsons, etc. So you can see in these pictorial figures that there are so many sources, and sometimes all these electrical equipment may get heated up. So the heat is sufficient enough to produce the spark. There are certain open flames. They are varies from to lit a cigarette to a welding activity. Mechanically generated. Now, why I'm talking about the welding activity? Sometimes if you are working in the combustible environment, and if because of a variety of reasons, wear and tear may take place in any equipment, and you need to perform the welding activity. So when you need to perform this welding activity, you must ensure that either your workplace is cordoned off, or you must ensure that there would be no chance of formation of any combustible mixture within the periphery. Now, another is the mechanically generated impact spark. The few example is that hammering or hammer blow on a rusty steel surface compared to the hammer blow on a flint stone. So spark may generated. The speed and impact angle between the surface and a hammer are important, and a 90-degree blow on the surface is relatively harmless. So you must know that at what point of time you must impact all those hammers to the surface required. Electrical spark, for example, a bad electrical connection or a faulty pressure transmitter. The electric energy content of the spark determines the effectiveness of the ignition sources. There are sometimes you may encounter the high surface temperature. This can be the result of milling, grinding, rubbing, mechanical friction, and in a stuffing box or a bearing or a hot liquid pumped into a vessel. But there may be enough sources. Then electrostatic discharge. Static discharge can be generated by the air sliding over a wing, or even the pipeline transfer of any hydrocarbon from one place to another place. Then adiabatic compression. Sometimes air is pumped into a vessel and a vessel surface heats up. Then again it may cause some adiabatic compression. Radiation, lightning, etc. Because in history there are so many accidents, they are attributed to these type of ignition sources. Then there is a chance of static electricity. It's a major cause of fire and explosion in many industry, and generated when fluid flows through a pipe or from an opening into a tank. Main hazard are fire and explosion from spark containing enough energy to ignite the flammable vapors. So you must know, and if there is any chance of generation of static electricity, the system must be properly grounded, bounded, etc. We will discuss in subsequent modules. There are so many piping systems, they are responsible for generation of static electricity. So in piping system, the generation rate and the subsequent accumulation of static charges are function of flow rate, liquid velocity, pipe diameter, and a pipe length. So as a chemical engineer, must know that what kind of parameter those who are impacting the the generation of static electricity in the piping system. Then filling operation. The turbulence experienced in the filling operation usually caused by large flow rate, splashing, free falling liquids greatly increase the charge accumulation above the liquid generated in the piping system. We will discuss this filling operation in subsequent modules. Filtration. Filter, because of their large surface area, can generate as much as 200 times of electrostatic charge generated in same piping system without filtration. And another important aspect is the auto-oxidation. The process of slow oxidation accompanying the evolution of heat, sometimes leading to auto-ignition if energy is not removed from the system. Liquid with a relatively low volatile, they are particularly susceptible to this problem. And liquid with high volatility are less susceptible to auto-ignition because they self-cool as a result of evaporation. So this is sometimes known as spontaneous combustion, when the fire results in oil on a rags in a warm storage area. Sometimes it is quite common when you store the oil bearing seeds in the closed silos, and sometimes because of this auto ignition ability you may experience the rise in temperature. Then sometimes spray and mist, they do contribute towards the generation of static charges. So static electricity is generated when mist of a spray is passed through an orifice. A charge may accumulate and a discharge in a spark. Now if flammable vapors are present, a fire or explosion will occur, and mist and spray also affect the flammability limits. So do care, because sometimes if you are spraying the inert material to a particular zone, then definitely you cannot overlook the importance of generation of spray and mist. So in this particular module, we have discussed about the various flammability characteristics, various aspects. We have gone through the different type of parameters and especially LFL and UFL, because these particular aspects are essential and important while designing the safety or devices in a particular workplace. Thank you very much.